All right, so today we are starting our unit on quadratics. Last unit, what function did you guys cover? What? Absolute value. So last unit was absolute value. This unit is quadratic. Now, what does a quadratic look like on a graph? Yeah, it looks like a U, right? Does anyone know the name of that shape? Parabola. It is a parabola. Good. So what we're going to do first to intro into quadratics is we are going to go over what the parent function of a quadratic looks like. Now, when I say parent function, what do you think I'm talking about? Yes. Parent function goes through 0, 0. Basically, no transformation has happened to it. It is the starting point. It is the initial, the plane quadratic. It does go through 0, 0. And who knows what the equation for the parent function of a quadratic is? Equals what? X squared. Yes. What makes a quadratic a quadratic? Yeah, the x is squared. What makes an absolute value an absolute value? Yeah, it has those absolute value symbols like that. So our equation is y equals x squared. Where is our starting point? Where's our initial change of direction for our parent function? 0, 0. This is called the what? The origin or the what of the quadratic? Vertex. It is the vertex. Who knows what point we can graph next? We can do that one for sure. Up 1 over 1. So we have negative 1, 1. Where is another point we can graph? 1, 1. Not quite. So we know that we can go up 1 over 1 and up 1 over 1. Perfectly symmetrical first points here, right? This is because it's the parent function. It hasn't been stretched or compressed. It's normal. Now, we know that the equation of a quadratic, the parent function, is y equals x squared. What is happening to the x? It's being squared, right? So if my x value is 2, what's my y value? 4. How'd you get that? Oh my gosh, you squared 2. So at 2, what's my y value again? 4. So it's not 2, 2, it's 2, 4. And if I'm at negative 2, what's my y value? 4 again. So at negative 2, our y value is 4. What about an x value of 3? Ah, yes, you get it. My y value is 9. And at negative 3, 9 again. And we can, oh boy, we can connect those points on the graph to create our parabolic shape, our quadratic. And there it is. That's our parent function. Y equals x squared. So over here, some info about this graph. We're going to do domain and range. Let's do domain first. Domain is which values? X or Y? X, good. Domain is X. Now, we're asked to write both the set and interval notation. What does set notation look like? Yes, it has squiggly brackets, I call them. Turns out, just learned yesterday from a student, they're called French brackets. I just call them squiggly brackets. It's easier to remember. Now, we know that domain is x's, so how I like to figure out domain and range is I ask myself first, what is the least x value for this graph? When do I stop going down? I never do, yeah, it's negative infinity. What is my greatest x value? Positive infinity. Or in other words, x is All real numbers, good. So my set notation starts with a squiggly bracket. Then what do I put? What do I put if I know x is all real numbers? You could, right, you put x, and then? X is an element of or in all real numbers. Do you guys remember that? So, did she teach you this middle symbol here?
We talked about it briefly, but she
Okay.
used it in it twice.
Ah, so this? Yeah. That's like really extreme shorthand. I don't think that that's what pre-cal wants. I think they want this. So we're going to do this. This is epsilon. It just means is an element of, or you can say x is in all real numbers. The way that you write this is like a C with a line in the middle. Okay? And then you close it with a squiggly bracket. Now, interval notation, what does interval notation look like? Parentheses, good. So, we said that our lowest value was negative infinity and our max value was infinity. So, am I going to start off with a parenthesis or a straight bracket?
You always use parentheses when you use infinity.
Yes, and why do we use parentheses when we use infinity?
Because it's not defined.
You can never be negative infinity.
Definite.
Yes, you can never touch negative infinity. So we put a parenthesis, meaning it's not equal to negative infinity. And it goes from negative infinity to positive infinity, and then what do I put? Parenthesis. Beautiful. And range is which values, x or y?
Y.
Yes. Now, as always, I ask myself, okay, what is the least y value here? 0, right? I go to 0 right there on the y-axis. I go down to 0. Is it equal to 0? Am I touching 0?
Yes.
Yes, I am. I have a point right on 0. And then what's my max y value?
Infinity.
Infinity. So I go from 0 to infinity, or in other words, y is always
Positive.
bigger than, greater than or equal to 0. Yes. So I start off my set notation with a squiggly bracket. Then what do I put? That's set notation. You just always start off with a squiggly bracket. Okay? Yes. Does anyone know what this line thingy means? Sometimes, if there was another one, it would be absolute value, but not in this case. It's just the symbol for such that. Such that. Such that. And then y is always what? Beautiful. And squiggly bracket, done. So, I will also accept if your brain doesn't really think that way, oh, y is always greater than 0. What you could do is the full interval. So, y is bigger than or equal to 0, but it's less than infinity. That is also correct. Is it more writing? Yes. It's more writing. Now, unfortunately, this is shorthand, okay? This is like if you were writing a note to your friend, this is how you'd write it. Yes?
If you don't put, you said you don't have to do more writing and you don't have to put the infinity.
Right.
If you don't put the infinity, is it just assumes that that's infinity?
Yes. It's everything greater than 0. Everything greater than 0 goes to infinity. Now, if you are going to go some type of math route in college or engineering or physics, this really isn't accepted. What is accepted, the most formal way to write set notation here is you put y is an element of all real numbers, such that y is bigger than or equal to 0. We're just adding in that element of all real numbers here. I'll accept either one of these. Just know that this is the most formal way to write it. All right, so then interval notation. Yes. What is our lowest y value? 0. Is it touching 0?
Yes.
So what do I put? I put a bracket, 0, and then what's my max value? Infinity. And I put a parentheses. Yes. All right. So now, just a couple of loose ends here. What was the vertex of our parent function? 0, 0. What is the x-intercept? 0, 0. Right? That's where it intercepts the x-axis. Where is the y-intercept? 0, 0. Yes. Is it a minimum or maximum point, the vertex? Minimum. Why? Yes, it's the lowest. So it's a minimum at 0, 0. Now, it's then asking for the axis of symmetry. Where is the axis of symmetry?
0.
It goes through 0, 0, yes, but what is that line called there? Yes. So the axis of symmetry is the line where you could fold this graph and have the graph line up. Ooh. Ooh. So you can fold it right here and have everything line up. So this axis of symmetry passes through which vertex? Which axis? The x. So it's going to be x equals something, and at what point does it pass through?
0.
So it's x equals 0. This is the line x equals 0. X equals 0. This is the, oh, come on, zoom in. What is going on? There we go. This is the axis of symmetry. Any questions about the parent function? All right. Now we are going to go over our transformations. So this parent function can be moved, it can be reflected, it can be stretched or compressed. All of these things can happen to this parent function to create a new equation, a new graph. Now, we know f of x is equal to x squared is our parent function. When we have values, when's this class end? Yeah, when's that end?
2:34.
2:30. Okay, so we have a half hour. Oh my gosh. Okay. So we have different values here that will either move it, stretch, compress it, or reflect it. We have A, B, H, and K. These values are exactly the same as they were in absolute value. And they are going to stay the same for the rest of the year, no matter what type of equation we have. So, does anyone remember what A does to our graph?
Stretch compression.
You're right. It stretches and compresses it, and if it's negative, it does what? Reflects it. Good. So, if the absolute value of A, meaning, forget about the negative, but the actual value A, the absolute value of A is greater than 1, it's bigger than 1, is it a stretch or compression? It is a stretch. Is it a vertical or horizontal stretch? Vertical. A is always vertical. Everything about A is vertical. Which one is B? Oh my gosh. Which one is horizontal? Right. B is horizontal. So, A, when it's bigger than 1, is a vertical stretch, which, what is that going to look like on the graph? Is it going to be skinny or wide? It's going to be skinny, very skinny. So if you want, you can sketch a little tiny graph with a really skinny quadratic. That's a really bad sketch, but you know, as long as you know what it means. If A, the absolute value of A, is between 0 and 1, meaning it's a fraction. So if A is a fraction, is it a stretch or compress? Compressed. So it's a vertical compression, meaning the graph is what? Wide or skinny? Very wide. So our vertical, that means up and down. If it's stretched, it gets really skinny. If it's compressed, it's getting fatter. If A is less than 0, which I don't like how that's written. Let's just, if A is negative. If A is negative, what does that mean? What's happening? It's reflecting. Yes, so it's a vertical reflection. And what does that look like? What does that look like on the graph?
Like an N.
Right. Well, actually, it reflects over the x-axis. It reflects over the x-axis. It's upside down now. Yeah, it looks like an N kind of. Like this. And then we said before, our B value is our horizontal stretches or compressions. Now, inside the parentheses is always what? Normal?
Yes.
So HX normally, left and right, when you're moving left and right, that's normal? No, right? It's backwards from what you think. Inside, I think she called it tricky, right?
Yeah.
Yes. Inside the parentheses is always backwards. So is B inside our parentheses that are squared?
Yeah.
Yes, it is. Meaning B is backwards from what you would think. So B, yes, B is everything backwards from A. So if B is greater than 1, what does that mean? It's a horizontal compression, yes. Horizontal compression. Now, if I'm sitting here and on my horizontal, that means this way, right? I'm stretching and compressing my horizontal line. If I am, compressing my horizontal line, what's happening to the graph? It's getting skinny. So we have a little skinny graph. If B is a fraction, it's between 0 and 1. If it's a fraction, is that a stretch or compression?
Wait, I picked this up first, so it's just like a horizontal compression.
Yeah. Ah, good. That's what makes it tricky. In this class, we will never ask you to look at a graph and tell us whether it's a vertical stretch or a horizontal compression, because they do look the same. Okay? They do look the same. Good question. So if B is between 0 and 1, meaning it's a fraction, so it's less than 1, and remember it's backwards from A, is that a horizontal stretch or compression? It's a stretch. Meaning, on the horizontal, I am now stretching it outward. What's happening to our graph? It's getting wider. Again, it looks exactly like a vertical compression. It's wide. What if B is less than 0? What do you think that means? If B is negative, it still reflects it. Ah, well, no. It's a horizontal reflection. No. Right. The reason. So listen. If I am taking my quadratic and reflecting it horizontally. Okay, so here is my quadratic, and I'm reflecting it. Can you tell the difference? It's still the same shape because it's perfectly symmetrical, right? Because it's perfectly symmetrical, it is the exact same. Literally, there is no difference. That's why we really don't talk about a negative B. It looks the exact same. That's why she said that. That's why she said there's never a horizontal reflection.
So that group B reflects over the y-axis.
Yes. In later units, there is going to be a horizontal reflection because not all of our graphs are symmetrical like a quadratic is. For instance, a cubic, this thing, can for sure be reflected horizontally. That's coming up in a couple units. Don't worry, it's not hard. All right. H. So if I'm looking back at my function in vertex form, what does H do to our graph? Yes, it moves it left and right. It is a horizontal translation. I said vertical. It is horizontal translation. And if we have minus H, what does that mean? It moves to the right, yes. If it's positive, I'm sorry, my left and rights are really bad. So if it's negative, if it's X minus H, which way should it be moving? To the right, yes, good. And if it's plus H, it's moving to the left. Because it's backwards. It's inside the parentheses, right? It's tricky, like she said. K. Is K inside of our parentheses? No. So is it backwards? No, it's normal, right? And it's called the what? K is the vertical translation. Yes. It's positive. It goes up. It's negative. It goes down. Where is the vertex? Where's the vertex? It's at H and K. Which one, H or K, determines our range? K. K does. K determines range. Meaning, if your quadratic is not reflected, it's normal, it's facing upwards, our range would be y is bigger than or equal to k. If it's upside down, what would it be? It'd be y is less than or equal to k. But I won't write that. Axis of symmetry. Where is the axis of symmetry in terms of H and K? X equals H. X equals H. Why is it asking minimum or maximum? Oh, the minimum or maximum would again be HK because it is the vertex, right? Any questions about any of this that we've gone over? Yes? So minimum or maximum just means if the graph is normal, like this, it has a minimum. And that minimum point right there is HK. If it has a maximum, it's reflected, but still that maximum point is HK. Oh, yeah, I'm just showing you. You don't have to write that. Yes. 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 Any other questions from these notes? Again, almost all of this was the exact same as absolute value. Every single unit, the very first day, we're going to have a day on transformations, and it's going to be almost exactly like this. All right. I need to show you how to find the stretch or compression number on a graph. Because unfortunately, a lot of you guys half the time get it and half the time are guessing. Okay? So I'm going to give you a graph, and I'm going to give the easy one first. Who knows how we find, is this a stretch or compression?
That is a square.
It's a what?
Stretch.
It is a stretch. Good. How do we find the A value?
It's
When you are looking at a linear line, how do you find the slope? The slope is always what over what? Rise over run. Well, this is not a normal linear line, right? It's y equals x squared. What's happening to the x? What's happening to the x?
It's squared.
It's being squared. So which one is the x value? The rise or the run? Which one's the x? The rise or the run? The run. So, because x is being squared, to find the slope of a quadratic, it's rise over run squared. So, what's the rise here?
2.
2. What's the run?
Oh,
1.
1. But we have to square it. Well, what's 1 squared?
1.
1. So what is our slope? Our a?
2.
2. Easy peasy. The reason why I tell you to do run squared is because of this. This is a stretch or compression.
Oh,
Compression. Who knows by how much?
Wait, how? Wait. 5, 4, 2, 1, 2, 2 over 2.
Okay, so what's our rise?
2.
What's our run?
2.
But what do we have to do to our run?
Squared it.
So it's 2 over what's 2 squared?
4.
And what is that? That's how you find the a. Any questions there? So just always remember, square the run in a quadratic. Square the run. So it's rise over run. Run squared. Oh my God. Rise over run squared. Any questions here? All right, go ahead.